project. This is a 500 level class. So one of the most important part of the 500 level class is to make sure that you have an opportunity to take what you learned in the class and apply it to research style projects, so that you can have some real good insight into how these the advanced material can be applied in a research setting. Years in the past, we have primarily run 508 project with essentially having each of you to propose some kind of a GPU usage in a application or in a research project, and sometimes the professors in different groups will come and propose a couple of problems that they would like to move the computation from CPU to GPU, and then we have a few groups form. The problem with that approach is that sometimes me and the TAs are also learning about the problem. So sometimes we cannot help you too much with some of these research problems. And so there was one year we had to learn about quantum chromodynamics first, and then by the time we figure out what it is, we're already almost at the end of the semester, right? So that was not exactly efficient as the way of learning. So this semester we're going to try something new. As I mentioned last time, many of you are Master of Engineering students. So it's also going to be hard for you to come with your own thesis problem, or try to work into a big research code and try to parallelize and improve some of the code. So over time, we have worked on several interesting computation types, and these computation types are very challenging for GPUs. And in fact, in the past several generations, the GPU hardware has been evolving, and NVIDIA, has been well aware of some of these challenges, and my group has been also collaborating with NVIDIA, or competing with NVIDIA in some ways, and IBM, so that we can take these problems and solve them in a way that is more appropriate for GPUs, and also help the GPU hardware to evolve, and so that the GPU hardware will also become more amenable to these applications. So this year we're going to do the following. We're going to suggest 2 to 3 kind of problems. These problems are cutting edge problems. So one of them is the graph, the graph analytics problem, and then we have an active DARPA challenge that is going on every year, and some of my students have been participating in that challenge. So so we actually know quite a bit about this problem, and so we would open it up for class here, that you can form teams, and then you can begin to look into one of a problem like this. So you could choose the graph challenge, or you could choose one of the other one of the 2 other problems, and then this way we know a lot about the problem, so that we can give you better advice, right? And then you can work on this, and then we can also provide you with some of the basis, so that you don't have to totally start from scratch. So that you don't have to build a lot of infrastructure to be able to to even get into the problem. So that's the idea. So today, Carl Pearson and I prepared some slides, and Carl is going to present the project, and then we're going to actually get. Are you going to present, or Zed?
Zed.
So Zed is going to present one of the interesting direction of extending from the triangle counting code, and as a way for you to see, you can potentially work on some core algorithms, and then we can potentially extend it in one of the several possible ways, so that you can work into even more research-oriented activities, right? So, Carl, why don't we start with you?
Okay.
So I can run the slides for you.
Oh, okay. Well, great.
This is how it works. the best, let's see.
Okay, so Professor Who mentioned some of this stuff, but right, the goal of the course project is to be somewhat substantial. Sorry, I'm going to turn and face you in a second. And so, in the past, we've done some work with scientific applications or high-performance computing applications where maybe some patterns of the application were amenable to acceleration on GPUs, and we asked the students to take that from their own research area and try to accelerate them. We're starting to look at some applications where GPUs haven't taken as much of a foothold and try to make it more accessible for people to use GPUs on some of these computation algorithms. And particularly, we're kind of interested in graph algorithms. So based on what you've learned in this class, I think you can take some of the algorithms and approaches that you've learned and apply it to some of these problems. And the basic idea is that when you're working on accelerating these algorithms, you want to be thinking about the relationship, not just the algorithm and whether the algorithm itself is an efficient way to solve the problem, but the effect of modifying the algorithm so that it is more amenable to GPU execution may negatively or positively impact sort of the beneficial properties of the algorithm or the computational properties of the algorithm. And depending on the problem that you're working on, the properties of the graph, say, that may or may not be worth it. But these are the kinds of things that we want to evaluate. There's probably not a sort of one-size-fits-all solution for these sorts of data-dependent computation problems that when you look at. So it's kind of another added dimension. You're not just figuring out the algorithm and the hardware, but also the pattern, the shape of your data is going to impact the performance of the application. And when I'm talking a little bit about the triangle counting, which you did in an MP, I know, but we have some more detailed information about it. I think you'll see why that might be the case. So, particularly in this problem, I think we've talked about some of these. I know that when I was in here giving the early lectures in the class, we talked about the global memory bandwidth problem, right? We had like the dam spillway, I think was one image, and straw was the other one. So frequently when we're working with GPUs, the ultimate problem that we face, or one of the ultimate problems that we face, is global memory bandwidth. And so depending on how much attention you were paying while you're doing the NPs, you may have noticed it, or may have noticed this, or possibly not if you didn't do any profiling. But it's just because a lot of tasks, right, we go to a lot of effort in this class to try to capture reuse in the tasks that we do. So right, when we're doing the register tiling and the matrix multiplication and other things of that nature, all of the effort is really in capturing reuse or making the global memory access pattern better. And that's because this is a fundamentally limiting problem. But if you're doing a problem where there just isn't much reuse, or the reuse is very difficult for you to express or anticipate ahead of time, say because whether or not you're going to reuse a piece of data depends on the shape of your graph, then it can be very difficult to capture that reuse in your code. So that's one challenge that we have. And so another problem that we face is kind of related is that if there's some kind of global synchronization that needs to be done, so across all of your cooperative workers, if you have short-lived kernels, so if you have some kind of iterative algorithm, so say if you're doing, right when you implement the breadth-first search, that's just a single wavefront, right? So we have a list and we get all of the neighbors. So if you wanted to traverse the whole graph that way, you would do many, many, many kernel launches, right? And the cost of doing that kernel launch can be as expensive as the cost of doing the traversal. And so if you need to do this sort of frequent synchronization, that can be very expensive as well. And so many iterative algorithms have this property. There are some techniques that people do, so you may be able to get away with sort of being relaxed about when you synchronize, accepting some error in each iteration, which will cause you to take more iterations to converge, but if you don't have to synchronize as much, you can get through the iterations faster and ends up being worth it, that kind of thing. And particularly when we're looking at the graphs, I would say this data-dependent parallelism is going to be a big problem. I'll give some concrete examples of this, talking about the triangle counting. But it may be that you want to do a particular task on some pieces of data, but you don't know how big that data is going to be until you get there. And if the data is big, you want to use a lot of parallelism to solve it. And if the data is small, you want to use not that much parallelism to solve it. Right? You want to make full use of the parallelism in the hardware. But I mean, you might be thinking right now that you don't know how to write CUDA code to do that, right? You assign your threads, you have a fixed amount of threads that you assign to each task, and that's all you have, right? So figuring out ways to tackle this problem, probably we've talked about dynamic parallelism, where threads can launch their own kernels, you can add more parallelism, but maybe there's other things to do. So these are some of the problems that we expect you to sort of face. So in the past, when people have taken this project seriously in this class, I'm sure it's led to contributions to publications that we don't know about. But we have had former students turn the projects in this class into serious, research that's generated multiple papers and generated software tools that people actually use. So this is a magnetic resonance imaging reconstruction on GPUs. I don't know if you want to talk about any more things.
We're good because we're using a different model this semester.
Yeah, so but I guess the point we're trying to make here is that, if we take this project seriously and really get into it, you'll probably be doing something that hasn't been done before, or you'll be doing it better than anyone has done it before. You now know enough about CUDA and parallelism to do that. That's the level you're at now, that you've done this class. So
there are more than 300 citations out of those papers now.
So there you go. So we're going to talk a little bit more about the project ideas in a second, but if you're going to take anything away from this, take away this, which is that 2 weeks from today, this is what you need to have formed into a team and done this so that we know what your project is going to be about. Okay, so I mean, you can kind of, so we want to know what the project, sorry, this mentor thing is a typo. We have a different model this year, but what your team wants to do with the project, what resources you're going to leverage to do the project, so whether that's some pre-existing code or some paper that you think has a good approach that you want to expand on, whether you have any particular background knowledge or algorithm that you're trying to implement, something along those lines. Right, and so then the resources that you want, if you could make that available to us, that would be wonderful. And then of course, who's in your team. And so what we think you should do over the next 2 weeks is come and talk to the course staff in office hours. And so we're not going to put this all one way. I'll probably be holding some office hours too. And I don't have those scheduled yet, but we'll come up with the time. Maybe it'll be on Tuesday before class.
Because I do it before Thursday, and you can do Thursday.
And then, if that doesn't work for you, we can probably find another time.
How many people can we have?
2 to 3.
2 to 3? Okay. And so that way we can talk about what kinds of things you want to tackle, what approaches you're thinking of, and I can maybe guide you along the way a little bit. So there's going to be, I think this is going to be when the presentations are, right? Yeah. So over 2 days, we're going to have everyone give a relatively short presentation about, what they did and what their results were. So, don't embarrass yourself in front of your friends. And a week later, the final technical report on everything. And so I think we'll release some more specifications for what we expect for these 2 things. But I think you can probably imagine. Right?
Are we limited to just using Rye as a submission thing for projects?
Yeah, I suppose so. Yeah. I mean, I don't think we can make any other resource available to you. And it would be, I guess I don't want to speak for you, but if you have some particular idea and you have access to a system, maybe that's okay.
We'll talk about Rye a little bit more anyway.
Yeah.
So ask again. Okay.
Right, and so Rye is probably a little more configurable than you have been taking advantage of, and I'll talk about that a little bit.
Yep.
So that's what we're going to talk about now. Good question. But first, so we'll talk about Rye, but the other thing that I want to point out is this research group has published other benchmark suites in the past. And so we don't necessarily think that you should take one of those things and try to improve on it, but you can look at some of the computation patterns and collaboration patterns that are used in that code. And also if you look at that code, you might learn something new about ways you can write CUDA. So that's the point we really want to make here. But we can talk about Rye. Okay, so you've all been using Rye unlike past years, so you're already at least somewhat familiar with how it works. Basically, you just you have been using Rye to, you fill out the little pieces of the code where we told you to, and you submit it without really changing anything, and it runs some tests and it works for you. But really, Rye is sort of an environment where you can define any set of operations you want, and then you can also define the environment that those operations are executed in. And so we've just defined environments for all of the MPs and then written most of the code for you, but really,
As a template.
yeah, as a template, but really you can define all of your source code totally from scratch, and also the environment that it's executed in completely as you desire. So if you're trying to do something different with the project, then you can probably do it through Rye. You can define an environment that has the data sets that you want in it. You can build it with the arguments that you want, and with the build system that you want, and so on and so forth. You'll have to set it up to work that way, and I'll kind of show you how you can do that.
By
Yeah.
the way,
this-
the last bullet is a typo again.
Okay.
Just also mentioned that students can also use a Docker of their choice.
Right, exactly. So we're going to talk about that, because that's how you set up the environment the way you want.
Okay.
So Rye, basically what happens is this is you, and then whenever you submit a job, it uploads, maybe you gathered this when you ran it, but when you upload your job, it says it's uploaded your build folder somewhere. So when you submit a job, it uploads your build folder somewhere. And this is on AWS, I think. And then it submits a description of your job, so that's kind of what it takes from the Rye build into an AWS queue. And then one of the servers will accept the job from there, and it'll say, oh, to run this job I need a particular uploaded file, and I'll go and grab it, right? And then when it's done executing, it stores the environment in here, back in AWS, so you can retrieve it, right, and get your results back. And then this is where we store your grades and stuff. So that's how it works. So when you're using it, that's exactly what you'll be doing. No, it's all right. And so what we do for the environment in Rye is that everything in Rye executes inside a container, and it uses Docker, which probably most people have heard of, but maybe not everyone has used. So you can kind of think of it as a lightweight virtual machine. And so basically, instead of having, it doesn't use, it uses the same kernel as the existing operating system, so you don't sort of have a whole new operating system running on top, but it's sort of a unique and contained environment that then you can configure however you want. So basically, these bins and libraries and applications and stuff, right, you can control, you want CMake 3.9.2 because you use a particular package in your project that, only works with that, and you want to build with these particular flags. So you can configure all of this exactly the way you want in your project. And so the way you're going to do that is you have to write a Docker file. And so this is a little hard to see, I know. I'm going to update this slide. I was hoping to do it this afternoon, but I didn't get to it, with an example of where you can look at this Docker file online. If you haven't written a Docker file before, it's not really that complicated. Basically, all you're doing is specifying a recipe that configures the environment the way you want. So, for example, this file at the top there, it says from, and that says which environment this Docker file uses as a base. So this is actually the Docker file that is used for the triangle counting lab. And so it starts with a different Docker file that I defined that includes the pangolin library that is used for building the vectors and reading the graphs and stuff. But you could start from a Docker file that's kind of like Ubuntu with nothing added, which might be a good place to start. And then you can see that the first thing it does is it runs apt update and apt install, and it installs curl and gzip so that I can download the graphs data sets from Amazon that your MP executes against. So you can set environment variables, and it just sequentially executes all of these steps, and then at the end, the image that you run in is the state that the Docker file is left in. So after we've done all this, we've installed some packages, we've set some environment variables, we've created some directories, downloaded and extracted some stuff, and then when you run the code, we installed CMake, and then when you run the code, it sort of starts from that point, and that's the environment you're in. So if you wanted, you could create a Docker file that installed CMake, downloaded a few different graphs, maybe you tweak the graphs a little bit so that they're easier to consume in your C code, you don't have to worry about it. You can configure your build or something, or change something about CUDA, something like that, and define the environment the way you want. Probably what you'll mostly be doing is if you have some particular data sets and you don't want to download them every time, you can set up a Docker environment, and so the first time the server encounters your Docker file, your Docker environment, it will run it and download it, and then in future times you won't have to re-download those data sets every time.
Are we going to use our internal servers or AWS?
I don't know.
We will know in a few days.
Just a heads up. If people are going to use ImageNet, which is about 1 terabyte, we may not be able to support it.
Right, that's
Yeah.
true.
Yeah.
So that's a good point. So yeah, if you're downloading like a ridiculously large data set that's like tens or hundreds of gigabytes, or maybe more than tens, but like 100 gigabytes, we might have to think a little bit more carefully about that. But yeah, hopefully it should work for small enough ones. Hopefully the small enough
For
ones will be good
testing
enough.
projects, we may not go there.
Yeah. So yeah, so this is how you can configure it, and we'll post the updated version of these slides that has the link, so you can browse it. So yeah, next.
Yep.
And so you've been using this RAI build file, right? But usually you aren't in the MPs. You're not modifying this. Maybe you modify it if you wanted to test or change a little something, but we've really never required you to run it. Oh, so can you go through all the animations actually?
Yep.
You just go all the way to the end of all of them, whatever. Yeah, just so we
This
go.
is it.
Okay, so but the important thing is that you can change the base Docker image that you're using, and actually I should probably update this so that I show you how to use RAI to build the Docker image also, because that's what you'll need to do if you want to create your own environment. But then these commands here is just what's executed in that environment, and they're just executed in order. So you might have a different compile command and a different run command, and then you might change it so you can profile your code or something to get the results, right? So you can modify this build, this RAI build file, and it'll do whatever you want. I mean, you can mess around with it. If you need network access for some reason, you have to put this limits network true in. If you don't need network access, then it doesn't matter what you put there, I guess. So you can modify this if you want to make it do whatever you need done for your project, right? Okay, so yeah.
So a couple of things. The comment on the profiling and the capability versus debugging, right?
Sure. So RAI, as you have probably observed, is not an interactive environment, right? So we don't support using an interactive debugger through RAI, of course. Which is something that we'd like to support, but we definitely will not be doing this semester. So the difference between the profiling is that maybe in the past, if you've done profiling, you've been in a situation where you do it in a sort of interactive way, where you fire up this profiling application and you put in the binary that you're going to run in the arguments, and you click a button, you get a nice graph on the screen, you can futz around with stuff. So you can't really do it in the same style here. But what you can do with the NVIDIA profiling tools is you can run the profiling tools to capture sort of a profiling database, and then you can download the file from RAI. Right, RAI uploads the result of your run on AWS. You can download that, get that database out of there, and then open it up in the NVIDIA Visual Profiler, or use NVProf to consume the results. So that's sort of how you will profile using RAI. And I mean, we can probably give some examples of how to use the profiler, but I mean, if you want to know more, you can look
Yeah,
at the
we can probably
documentation.
even do a quick demo in one of the lectures after.
Yeah, sure, definitely. Yeah, we've done that before too, so.
Yep.
Yeah.
Okay.
So, but I think the profiling will be important for you to understand why the performance is the way it is on your code, right? Because the systems are kind of sophisticated, and it's tough to understand if you make a particular change why the result is what it is without looking at the profiles. Okay, so you already did triangle counting as an MP, but we didn't really require you to do much about it. So I can just talk to you a little bit about the sorts of directions you could go if you wanted to expand on this as a course project. So just a brief overview of the triangle counting again, right? The approach that we were taking for the MP is that if you want to figure out the number of triangles for a particular edge, it's the size of the union of the neighbor list for that edge, right? So if we're looking at edge 1 to 2 here, we can see that it should be part of 2 triangles. So it's this neighbor list of 1 with the neighbor list of 2, which is a size 2, so it's 2 triangles.
It's
Yeah.
intersection.
Intersection, yes. Thank you.
How do we turn it
Uh,
around?
It's going to be, I'll
Okay,
have to
we'll
fix it
fix it.
tonight. Yeah, sorry. Intersection, thank you. I definitely did not make these slides in a big hurry. So, right, if this is our directed graph, it's, in our case it's an acyclic graph, then we represent it as an adjacency matrix, right? So this is just a matrix where if you have an edge from I to j, it's not 0, and all of our edges are unweighted. So we just put a 1, otherwise the entry is 0. And then we use compressed sparse row format for that. So we have one array that says where each row starts, and then the column indices for the non-zero entry in that row. And then typically you would also have a data array that has the value of the entry for each non-zero, but all of ours are 1, so we just omit that. So if it's present, then we assume it's 1. So back to the triangle counting example, right? If we want to look at edge 1 to 2, we need to get the neighbor list for 1 and the neighbor list for 2. So in the adjacency matrix, it's these non-zeros, right? So representing, 2, 3, and 4. Edge from row 1 to column 2, 3, and 4, and row 2 to 3 and 4, right? So that is this data in the CSR, right? Okay. So again, this data in the CSR, and again, intersection. Thanks, Vikram. So ultimately what you're trying to do is find a fast way to count the size of the intersection of these 2 lists, right? The 2 pieces of this array. And so if I was working on edge 0 and edge 2, it would still be this piece of array, but it would be a different piece of this array for the first one, right? So the piece of the array depends on which nodes the edge is, source and destination. So when we had, so next slide, I guess is fine. So when we had you do it, we made you implement this first approach, which is basically where, when I look at these 2 lists, so these are our 2 lists here on the right side of the slide, what we do is we start with a pointer to the head of each list, and you increment the pointer to the smaller value every time. And then if the values match, you say, oh, we have a match, and then you increment them both. Right, so that's the first approach. You can tell that if this is A and this is B, you have A plus B loads, or maybe it's not that many loads, but you're making accessing that many elements in your array. And there's no parallelism, right? We have one thread doing this traversal over the entire array. So the plus side is that we have A plus B loads, which is pretty good because we're only touching each element once, but the downside is there's no parallelism, right? The only parallelism you get is across edges. So there's other approaches you could take. So for example, we could do, for every entry in A, we do a binary search against B to see if it's present, okay? So some of the entries will be present and you'll find it, and some of the entries won't be present, you won't find it. So the plus side, the pro of doing this is that we can in parallel look for every element of A in B at the same time, right? And if you do it that way, if you implement it this way, you can see that we're going to have more loads because we look at every element of A, and then, right, we load every element of A so we can see what we're looking for. And then for every element of A, we do a search through the length of B. So now instead of A plus B, we have A plus A log B accesses. And if A or B is large, this is smaller than A plus B. If A and B are large, it's bigger than A plus B. But on the plus side, we get A parallelism back. So that's potentially good. So that's another approach that you might consider investigating. whether that's worth doing or not. It seems like it could be worth doing sometimes on paper. So what you can do is you can actually optimize this a little bit more, because ideally we'd like to go back and recover the fact that it's A plus B loads only, but also somehow keep the parallelism higher than 1. So what we can do is, instead of having one thread do a binary search for each element, we have a thread handle multiple elements. And so instead of the thread looking for 1, and the thread looking for 7, and a thread looking for 8, you have a thread that's responsible for finding 1 and 7. You have a thread that's responsible for finding 8 and 10. And the thread looks at its first element and does a binary search to find where it is. So the thread's looking for 8, it finds that it's in here. And then it knows that if 10 is present in B, it's going to come after 8, because B is sorted. So the only reason most of these algorithms work faster is because these are sorted. So then you use this as a lower bound, and you just do a linear search from B for all elements after that. And so the nice thing is that we get a little bit closer to A plus B. It's kind of hard to tell from here, but basically if you have each thread doing C elements, you do A over C binary searches, right? Plus you end up looking at every element of A. Plus, in this approximation, we assume that the average thread looks through half of B. So you get a little bit closer to A plus B, but you, at the cost of a little bit of parallelism. Instead of parallelism A, you have A over C. So this is another approach that you could potentially check. And then sort of an extension of this is that in addition to doing, yeah, go on.
Basically, if you make C close to A, right?
C, yeah, so C,
then
if you make C big.
Yeah, it becomes A plus B, because the first one is log 2B is much smaller, and then the AB divided by C becomes B, right?
Yeah. So, right, if C was as big as A, you would do one pointless binary search, and then the normal linear search. So it'd be close to A plus B. So this is another option for the triangle counting. So I don't know if anyone actually ended up implementing more triangle counting kernels or not, but this is what you could have done. So related is, instead of just finding the lower bound of your chunk, you can also find the upper bound, so you don't have to search through the rest of B, you just search through part of B that your element could possibly be in. And so this gets a little bit closer, so you can tell now that you have to do these two binary searches for A over C, but you're going to touch every element of A and B only once now. So we're just a little bit above A plus B, but again, we have reduced our parallelism by C.
Actually, that's not clear to me at all. It's not clear if the upper bound would help.
Well, so yeah, it depends, because if the biggest entry of your chunk is bigger than B, then you'll search all the way to the end of B.
Right.
Yeah. If it's lower than B, you will.
But in that case, what is the binary search about? It will tell you these things.
Oh, because as soon as you get to the end of A, you know you're done.
Yeah.
Yeah, that's a good point.
Actually, in my you just answered my question.
Yeah.
Okay, good.
All right, think about this.
Yeah, because if you know that the second one, the upper bound is beyond B,
Yeah.
that means that you don't need to search it.
Right.
Right. So that's why it helps.
Okay. Nice. So maybe you skip this one.
No, it helps.
Yeah.
So,
Oh,
it's
okay.
fine.
Okay. I'll think about it. So there's one final approach.
Real-time research.
Yeah, right. I'm going to give a talk on some of this stuff tomorrow at 2. You're all invited. The final approach, which I haven't entirely worked out yet, but I'm pretty sure works, and I won't go into detail, but I'm happy to talk to you about it more when we're sitting down, is you can treat this problem as if it was similar to finding a merge path between A and B. So the merge path between A and B basically says, what order do I take elements from A and B in order to keep the combined list of A and B obeying whatever the ordering constraint is. So in our case, later elements of A are greater than earlier elements of A. So you would merge A and B together and keep that constraint. And the merge path tells you which order you should take elements from A and B in order to keep that constraint. And so whenever you have a tie in your merge path, so say So this path represents taking 1 from A, then 5 from B, then 6 from B, then 7 from A, then 7 from B. So you could have taken 7 from either A or B and kept this ordering. And so the number of ties that you have to break in your merge path is the number of common elements between A and B. And so what you can do is, when you parallelize merge path, sort of the traditional approach to doing it is we define some particular chunk size, so say C would be like 3 in this example, and we're going to say each parallel task is responsible for merging a total of 3 elements, some number from A and some number from B. But it could be 3 from A, 0 from B, it could be 0 from A, 3 from B, but you're going to result in 3 in your result. So then the trick is you have to figure out where you start looking in both A and B so that you know which elements to take. And you can basically figure out where you start at A and B is the point at which these diagonal lines, so this is the first 3 elements, the second 3 elements, where these diagonal lines cross the merge path. And you can find where the diagonal lines cross the merge path with a tweaked binary search that's sort of jointly between A and B, but it's like a one-dimensional binary search. It's kind of cool. I don't have a good slide to describe it yet, but I can talk to you about it. But I think the nice feature of this is that the parallelism that you get is A plus B divided by C, because it depends on the sum of the 2 lengths between the 2 lists. And so you have A plus B over C binary searches, the length of which could be up to A plus B in some cases. But then you end up touching every element at A and B only once other than that. So basically what you do is you figure out where these points are, and then, for example, from this point, I need to look at this chunk, so it's these 2 elements from A and this 1 element from B. And so so this thread will just be looking at those 3 elements, and then you can do a sorted search on these however you want from any of the previous methods that I talked about. So I think this is kind of maybe the most graceful way of implementing this. It's a little more complicated because it has more operations, but sort of algorithmically, you get A plus B over C parallelism, and you get pretty close to just A plus B loads. So this is something that I haven't implemented this yet, but probably I will by the time you come and talk to me about it. So, so if you're just tired of triangle counting, there's something that's a little more interesting that people generally are interested in researching, which is called Triad Census, which is counting all of these different sort of 3-node subgraphs, the population of these 3-node subgraphs in a big graph. And the reason people care about Triad Census is because they've observed that if your graph has proportionally more 1, 1, 1 U's than you expect, and proportionally fewer 1, 2, 0 U's, then you can make some reasonable guesses about various properties of the graph. People don't really fully understand why, but they understand that the Triad Census can tell you meaningful information about the graph. So you can see that the triangle is one of these. It's
Do you want to explain the meaning of the numbers and the?
So I don't have it on the top off the top of my head. But the C refers to whether they're the numbers and letters have meaning and it's unambiguous. The C I think means that it's a cycle, and the D means it's directed. But yeah. I haven't started generalizing our high performance triangle counting code to this yet either, so I haven't looked into it too much. But you can imagine that the kinds of simple traversals that we do in the triangle counting could probably be directly adapted to find some of these triads, and maybe other triads you could have a similar approach. And I'm not 100% sure, but I think there's limited prior work on doing this Triad Census on GPUs. So that would be something kind of interesting potentially. And so, aside from this, what I'm kind of expecting that you could investigate when we're doing this triangle counting stuff or Triad Census stuff is that if you implemented all those different triangle counting methods, you'd probably find that some of them work better on some graphs than others. And so you probably don't, understanding why the performance is on those particular graphs is probably interesting. The effect of how the graph is stored is probably interesting. So we use CSR, but you don't have to use CSR, of course. And maybe for different parts of your algorithm, you would want different structures. If your graph is not a directed acyclic graph, then you can't use the approaches that I described, or you can, but you have to modify them in some way. So that's potentially something to think about. You can order, if you do have a directed acyclic graph, you can reorder the nodes, which changes the topology of the directed acyclic graph and can have a big impact on the performance. So that's something you could look at. Which intersection algorithm is right to use at which point in time for the specific part of your graph you're looking at is probably not set in stone from the very beginning. So you could figure out a way to dynamically select that. Maybe you could use dynamic parallelism. Maybe you could have a monolithic kernel that at every time decides which it should use. You could look at the effects of moving over to multiple GPUs. So we're looking at this now, and some of the problems that we're running into is that sort of the fundamental triangle counting operation is so fast that any costs that you incur when trying to move it over to multiple GPUs can cause the triangle counting part to not be overlapped effectively, so it doesn't appear that you get any speed up even though all of your kernels are shorter. And then there's other triangle counting approaches. So there's sort of subgraph enumeration and just direct linear algebra approaches that I can tell you a little bit more about if you want to just try something totally different. So for example, you can count triangles by doing sparse matrix multiplication, which is kind of an interesting problem in its own right. So these are some other directions you could go with this triangle counting too, if you wanted.
Yeah, there could be even hybrid methods.
Yeah,
You could,
certainly.
do graph partitioning and using the DAX, and then you can
Right.
smaller subgraphs you can use linear algebra-based approach.
Yeah, so I mean, I think the design space of even just the triangle counting is quite large. So if you want to look at, you know, anything but use it. I mean, there are things you could do to speed up triangle counting potentially that are not related to optimizing a triangle counting kernel. Like you could do graph partitioning to partition a graph onto multiple GPUs and then pick your triangle counting kernel and say, we're just going to use this one, but can we do a better job, something like that. So you can kind of go a lot of different directions with this, and I'd be very interested to talk to you about anything that you find. And we could write a paper maybe. So I'm going to let Zed talk a little bit about K-trust decomposition now.
We could maybe even elaborate it just a little bit here. In a lot of methods, triangle counting is what we call these primitives, right? So these primitives can be invoked many, many times. So you could even, run the triangle counting once, and now that you have known, where the triangles are and so on, you could even reorder the nodes based on what you found out about the triangle counting, and then the subsequent passes will be faster, right? So there are all kinds of interesting, the algorithm techniques depending on the data distribution, depending on the use case, depending on how much information you know about it, right?
Yeah. So just like we teach some, like if you think back to 408, we kind of teach some basic sort of GPU parallel primitives. I mean, we don't necessarily always couch it in those terms, but like prefix scan. I mean, we use warp and block and grid reductions in triangle counting at various times. And so like being able to do a fast reduction is important for triangle counting. Sort of in the same way, being able to do fast basic graph operations is important for doing something more sophisticated. So that's why, it's like, why do we care about triangle counting? Well, we don't maybe per se, but we care, just like we care about fast reduction, not necessarily for its own sake.
Or even if you reconstruct a graph, prefix sum is a very important thing to reconstruct the CSR.
Yeah, sure. So,
Okay,
yeah.
is it? I'll continue to run the slide.
Sure.
So I'm going to talk about K-trust decomposition. Professor Wenbei went over it briefly.
Mic, up.
Better?
Yeah.
Yep.
So Professor Wenbei talked about this briefly. I'm going to go over what the problem is in more detail, but also go over two algorithms or very abstract algorithms. I'm not going to go over the parallelization of them. That's, I guess, up to us if we want to decide to work on this and how that works. So the problem of K-truss decomposition, let's first define what a K-truss is. So a K-truss is a graph such that every edge is part of K minus 2 triangles. So if you have, for example, this graph is a 3-truss, because every edge is part of one triangle. So that's the idea of a K-truss. These define very tightly connected components of a graph. So in order to figure out something like this, we need to reuse some of the stuff that Carl talked about, which is triangle counting. But it's a little bit different type of triangle counting. In the stuff that Carl was talking about, you need to get an overall triangle count of the graph. In K-truss decomposition, you want to get a triangle count per edge. So if you want to do that, you want to use the directed graph, whereas what Carl was talking about, an undirected graph, and whereas what Carl was talking about, you need to get a total order on the edges in the graph so that you get an exact triangle count for the whole graph. So that's one thing. The other thing is these algorithms are typically iterative, and this goes back to one of the things Carl was talking about, where you have to relaunch the kernel multiple times. For example, you have to relaunch triangle counting multiple times. And the way this is done is you basically are going to keep breaking down the graph until you have no more edges that do not meet the criteria that you're trying to fill. So here we have an example of a graph. Like I mentioned, this graph would be a 3-truss because every edge is part of at least one triangle. But if you decompose the graph and you remove these 2 edges, which are part of only one triangle, then you get a 4-truss because now these edges are only part of 2 triangles each. So that subgraph is called a 4-truss. So this idea of going through these graphs is the decomposition of the graph. You keep breaking down the graph until you get to the smallest possible subgraph where there are edges, and you still have a K-truss value. So for example, this graph has a K-truss decomposition of 4. So there's 2 algorithms I'm going to go over. The first one is the iterative triangle counting approach, and the second one is where you just update the triangle count per edges. So the first algorithm, this is actually one of the algorithms Professor Wenmei talked about before. What we'll do is we'll start with the example that we went over, that we just had in the previous slide. Let me know if this is big enough. So you start off with the graph, you do a triangle count on every edge. So in this case, 1, 1, 2, 2, 2, 2, 2, 2. And then what you see is which are the edges that do not meet your criteria. So the first, because you started out with k equals 3, all the edges meet your criteria, so this is a 3-truss. Now you're going to move to k equals 4. You're going to recount the triangles, or you can preserve the count of the triangles if you want. And what you're going to realize is that these 2 edges do not meet your criteria, so you delete those 2 edges. If you remove these 2 edges from the graph, what might have happened is that the edge count for one of the other edges might have been affected. So because you have possibly affected edges, you need to recount triangles in the graph until you have no more affected edges. So you have to recount triangles and delete edges until you have no more.
So that top horizontal one should be 3 to start.
You had 3 to start, sorry.
This is good.
So you keep counting triangles, finding affected edges, and deleting edges that do not meet your criteria. So when you have done that, and you still have a graph left, you know that that is that truss. Now, if we move to k equals to 5, what we're going to realize is none of the edges have 3 triangles, right? So you're going to remove all the edges. There's no edges left. So this graph is only a 4-truss. One thing to realize is we cannot just assume that this is a 5-truss from the beginning, even though there's an edge that has 3 triangles, because it's an idea of which subgraph meets the criteria of k minus 2 triangles. So that's the iterative approach of doing triangle counting multiple times. There's a couple of issues with this. Because of the fact you do triangle counting multiple times and you have to keep deleting edges from the graph, if you do not actually change your graph, you're going to be launching threads that do no work. Right? If you assign, for example, one thread to be counting triangles for one edge, if you're deleting edges, you're going to have less work as you keep going on. That's one issue. the other issue is, let's say you want to actually make the graph smaller. How do you do that in parallel? That's something called stream compaction, and there's ways to optimize that using prefix sum and things like that. So those are things you can think about if you're trying to solve trust decomposition with this approach. One more idea is, because you have to launch kernels multiple times, what if you don't do that? What if you actually just run one kernel that does all the iterations on the GPU, and the threads are just scheduling this and synchronizing on the GPU using cooperative groups, which is not something you've learned, but I think you can just easily find online. So the other algorithm, next slide, is another approach which is also iterative, but you do not have to recount triangles in this approach. You use atomic operations to decrement the count of triangles that each edge is involved in. So one of the problems, let's say if you go back to this approach where you assign one thread per edge, and you say, oh wait, this, for example, removing this edge is going to affect the triangle count for any other edge that is connected to, for example, this one, and this one. And let's say I just say, oh, I can just decrement the triangle count for each one of these. That's not actually correct because, for example, this is not actually making a triangle with this edge. So it's very hard to figure out from just the graph's information where each edge makes a triangle. So if you can enumerate all the triangles beforehand per edge, you know exactly which edges and which triangles to remove. So you keep track of all those and you just update the triangle list for each edge, and that decrements the count as you go along. So this requires a lot more memory, and it requires one extra step, which is enumeration of triangles, which is another problem that needs to be solved. Which is, to do that in parallel is very much like triangle counting, but you need to keep track of the list of triangles per edge, and you need to figure out how to store that in memory and how to actually traverse that and how to add triangles into this list. So that's the other approach. I don't think I have anything else besides this.
Do you really do the -1, or you remove the edge and then try to recount only subset of the?
Right. So I was just saying that if you wanted to just say some kind of simpler heuristic to say, okay, I want to just remove the decremented count. So what actually ends up happening in this approach is, for example, you know that this edge right here makes a triangle with this edge and this edge.
Yep.
So if I remove this edge, I need to remove the triangle. For example, if I label this A, B, and C, I need to remove the triangle A, B, C from each one of these edge lists, from each one of the edges that triangle lists. Sorry. So that's what you're actually doing. You're actually removing the triangle knowledge from the whole graph, which is not a trivial thing to do because like I mentioned, every one of these edges has that list. So first of all, creating the list is one problem, and then updating this is another problem. I think I have an example.
You have an example.
Yeah. So this is just the original way of doing trust decomposition. This is just talking about, sometimes you delete edges and then there's other edges that are affected. But I think you just recount. That's the trivial way of doing it. So if you go to the slide, this is the second way of doing it. So if you go to the next slide, there's an example. If you look at this graph, these are the edges. They correspond to the ones that are labeled here. And there's a triangle count, and then there's also a triangle list, which is just a list of the pair of edges that the edge makes a triangle with. So if you look at the animations. So you look at this, you're trying to see if this is a 4 plus. You're going to see that, for example, edge 2 only has one triangle. So you're going to need to delete this edge, along with update the triangle count for all the edges that is involved within a triangle. So you're going to delete this, decrement the triangle count. You see in the edge list that this makes a triangle with edges 1 and 3. So you're going to have to remove this triangle from 1 and 3's triangle list, which is this triangle and the next triangle.
That's why it's not as simple.
Right. And then now you can decrement those triangle counts.
And you propagate.
Right. So doing this serially is very easy because there's no issues of like race conditions. But if you do this in parallel, that becomes very, very difficult. And you just keep doing this for every one of the edges. So if you do this serially, it's very easy. But in parallel, it becomes very difficult. And the amount of memory you need for this is a lot because you do actually store the triangles. And then figuring out how to manage that is another issue. And that's pretty much it. I
think I'll probably do the domino algorithms for this. We can just kind of free out more and more.
Yeah, because you're deleting the triangles anyway, so you can compact.
Okay.
Yep.
For the example you draw on the blackboard, if k equals to 5, would that be the upper edge of the square? Because there are 3 triangles involved with that.
Sorry?
So
This
for
one?
For the k, yeah.
Yeah, so you're trying to say why is this edge not here for the k equal 5 case?
Yeah.
So the issue is you have to go iteratively through the k values. So when you, for example, are doing k equals 4, these edges go away. And you can only have a 5 truss if you have a 4 truss. And the 5 truss needs to be built from the graph that you have from the 4 truss. It has to be built on top of it. So there's other approaches you can do, which we're actually doing right now. You can talk to us about this, me, Vikram, or Carl, where you can do sort of a binary search to find this value as opposed to going through it iteratively. But then you need to keep track of, for example, if you go too far ahead, you need to keep track of the original case, so you can go back in case you go too far, delete too many edges.
So just to add, keeping track of where previous graph is where the trouble comes in, because keeping track of previous graph means you are actually having 2 copies of graph in the GPU level.
You can either have that, or you can have some other ways of managing that, right?
Yeah. So
there's some techniques to handle this. We are working on that too, so
Yeah, so don't panic if you don't see exactly how it works, because that's not the point for today.
Yeah.
The point for today is to show you a seemingly simple problem can actually have a very rich space of solution. Right. And if you're interested in this particular one, then we form a few groups, and then we can work with you guys, and then you guys can become expert in this.
dynamic partitioning.
Right, so there's other problems, I don't think we talk about this in this, but there's other problems too you can think about, which is like partitioning a graph. And
So we.
oh, you do have that.
Yeah.
Okay, that's fine.
Okay, so
Your turn.
So one other thing that we thought was kind of interesting was sometimes you have a scenario where the graph that you're working on is not static. So we want to support the case where we have some kind of graph and we want to know how many triangles it has or what the k-trust decomposition is. And then there's a sequence of edge updates. So maybe nodes are added, maybe an edge adds a node, maybe it's an edge between 2 existing nodes. I think a more difficult case is we could also consider that an edge or a node may be deleted. But basically the challenge here is you want to create a structure where there can be updates that are streamed into the graph and the GPU can still quickly support the operation in question. So obviously one approach, say if the operation we were concerned about supporting on the dynamic graph was triangle counting, one approach would obviously be we take an update in, and then if someone requests a triangle count, we just traverse the entire graph and count all the triangles again. But sort of like Zed was talking about with the k-trust decomposition, there's probably a way where you could keep track of how many triangles different edges are a part of, and if you add another edge, only increment a few things or something like that, right? So the challenge here is figuring out, A, what operations you're interested in supporting. That sort of constrains your design space a little bit. And then B, given those sets of operations you want to support, what is the right dynamic graph structure to do? And I think you could characterize this in a few different ways also. You might have something where edges are coming in on the CPU, and the GPU kernel is persistent, but needs to synchronize with the CPU somehow to do that. Or maybe there's some other approaches where kernels are launched to do batch updates on the graph, and you can do efficient operations between those batch updates, something like that. So this is a little more open. We haven't started looking at this as much, but there's definitely related work on dynamic GPU graph structures. And so I think then the question is probably looking at some of those, maybe you see some deficiencies. Maybe you think it's kind of interesting, but you'd like to look at doing multi-GPU for these dynamic structures. Or maybe you want to support some particular operations that they didn't really consider, something like that. So
You mentioned multi-GPU. Do we actually have access through Rive to
I
multi-GPU?
think so.
Yeah. There's no reason why you cannot use
Okay.
Yeah, so I think in that GPU field in the RI build, you just put like 2 instead of
Okay.
1. I think you can't do more than 4, probably. The systems are.
Right now it is 2.
Oh, you can't do more than 2.
And one more thing.
Yeah.
It might be restricted if you do not change the queue.
Yeah, that's the problem.
Okay.
So we'll have to talk to Andy on that.
Okay, sounds good. So it sounds like we can expect that 2 will work eventually.
Yeah.
Okay, great. In short order. So the other thing that we think might be kind of interesting is graph partitioning. And so the point I really want to make here is that graph partitioning, we're trying to somehow assign a label to each node or maybe each edge that says which partition it's part of. Now, why you want to do this is a separate question, but one reason is that the graph partition itself may be some kind of analysis of the graph, right? So like Facebook wants to figure out all the different little friend groups that are floating around in the US, right? And so that is a graph partitioning problem in some way. The other way you might want to do this is that you might want to partition a graph in order to make some other operation fast later. So you distribute the graph into turn the problem into multiple parallel subproblems. And so the algorithm, in the first case it might be that Facebook wants to use a particular algorithm to identify partitions, and so you would want to improve that, you would want to implement that algorithm on the GPU. The second case is more like you want to figure out a way to partition the graph that simultaneously allows you to speed up the operation that you actually care about, but the cost of partitioning the graph doesn't outweigh